Hey y'all, it's Becca. I'm a math, physics, and astronomy tutor here at Chegg. If you ever need such a tutor, feel free to hit me up on my profile that is linked below. But today I'm going to talk to y'all about diffraction gratings. Now you may have encountered diffraction gratings if you're taking an intro to physics class that includes optics and wave optics. But if you're taking wave optics, then you certainly will have run into the double slit experiment. Now, it turns out a diffraction grating is the same thing as a double slit experiment, except it's just like a zillion slit experiment. The condition to find a maximum fringe is exactly the same as it is in the double slit experiment. So those maximum bright fringes occur at integer multiples of the wavelength of light that's shining through the double slit or the diffraction grating. So here the m value is the order of the fringe, where the central max is order 0 and the fringes on either side go up in increments of 1. Lambda, of course, is the wavelength, and the angle is between the central max and whatever. And d is the slit spacing, or of course the spacing between, in the double slit, it's the spacing between the two slits, but in a diffraction grating, it's the spacing between all of the slits, the individual slits of the grating. So let's say that you're given a problem where monochromatic light is shown through a diffraction grating, and you're asked to find how many lines per meter the diffraction grating has, so essentially the density of lines in the diffraction grating. One important thing to note is that this is monochromatic light. That means that only one wavelength is being taken into account, and that wavelength, let's say, is given as 650 nanometers. So we have that value for lambda. And let's say that the figure you're given is this one, and it shows light shining through the diffraction grating, our central max here, and then our secondary and tertiary maxima are on either side. And the angle between the central max and the second maximum is given as 30 degrees. So the information that you know is that we have an angle of 30 degrees that brings us to our second max. So we can use that information to find the number of lines per meter in this particular case. So we don't know d yet. We're going to use d to find the number of lines per meter, but we're not given any value for slit spacing. If we were, the problem would be done pretty quickly. And then we have the sine of our angle, where sine theta is the sine of 30 degrees. And the order that we know about at 30 degrees is 2. And we know that our monochromatic light is a wavelength of 650 nanometers, which is red light. I did leave this in nanometers. That's okay for right now. It just means that the d value that we solve for is going to be in nanometers rather than meters. You can convert in the beginning or you can convert at the end. Since we're asked for lines per meter, I'm just going to convert at the end. Okay, so we know that sine 30 is 1/2, so we've got 1/2 d is equal to twice the wavelength. 2 times 650 gives us 1300. And if we solve for d, we simply have to multiply both sides by 2, which means that d is 2600 nanometers, okay? So 2600 nanometers can be converted to meters. Remember, a nanometer is 1/1000th of a meter. So a simple way, I suppose, of writing d in meters would be 2600 times 10 to the -9th meters. But we're not asked for d. We're not asked to find the spacing between each line, which is 2600 times 10 to the -9th meters, or 2600 billionths of a meter. We are asked to find how many lines you could find in 1 meter of diffraction grating using that slit spacing. Well, the number of lines n is given by just the inverse of d, because d in essence is the meters per line. The slit spacing can be thought of as meters per line, and if we're looking for lines per meter, we simply just need to take the inverse of that. And if we take the inverse of that, we get approximately 1.6 times 10 to the 5th lines per meter. So 1.6 times 10 to the fifth lines would fit in just 1 meter of that type of diffraction grating. These types of problems are very variable. They can give you the number of lines per meter and ask you to find the wavelength. They can give you dichromatic light and ask you to find the difference between, let's say, a red line and a blue line based on the order and based on the angle between them. There are lots of different ways to set up these problems. This is just one. And hopefully this helped you kind of give you the tools to figure out diffraction grating problems. So if you need any help with these kinds of problems, feel free to hit me up or any other physics tutor here on Chegg. Okay? Bye, guys.